Okay, today I want to talk about 3-1 factor and well, let's see. We had following lineup 3-0, 3 lambda, and 3-1. I want to know what your reaction. Which type is most difficult? Flow of weight is look like flow of weight is this C equal to L infinity x mu, and the flow, the non-singular transformation flow, that's the theta s, giving you theta s restricted on the center. 3 lambda case, the center is L infinity of R over Tz, e to the minus t equal to lambda. 3-1 case, C equals L infinity over dot, single point. What is your, don't hesitate, what is your reaction about the difficulty of attacking those cases? Which one you choose? 3-0. Yeah. Because it's 0? How about the others? 3-0. Because it employs the ergodic theory. Okay. Actually, indeed, 3-0 looks like the most complicated, but it turns out 3-0 has if you change the point of view, it gives you the lot of handles. Okay, and let me say the question first, open question. Okay, flow, the T of R of x, this is orbit of point x, and x, the m tilde, the core, is direct integral over the center. I don't like this write a measure because this does not depend on the measure whatsoever. So it's just an absolute measure class. Absolute value, the absolute continuity measure class. Okay, now for the orbit, if x, y in the same orbit of say x0, then automatically is that m of x, m tilde of x, and m tilde of y are isomorphic because theta or t sub s transformed one fiber to the other isomorphically. Okay, so that's another question. Is it possible to have the following: m tilde of x isomorphic to m tilde of y if and only if x, y were an orbit equivalence, is y is in the orbit of x. And so far nobody proposed a candidate that isomorphism equivalence equal to the orbit equivalence. Okay, this was unanswered. But now let's see. 3-1 factor. It's then if I have 3-1 factor, then what happens? Okay, so that's your core is a to infinity factor. Of course, you have trace, unique trace, and flow of weight, non-commutative flow of weight, tau of theta s equal to minus tau over tau. Okay, now you can raise the following question. What type of flow can appear here? Okay, that's the question to tackle. And the answer is every ergodic flow appears as the flow of weight, namely as a CRT. How do you do that? Okay. You need this 3-1 core. If you have 3-1 core, it's very easy to construct the core of 3-0 factor which has a given flow of weight. Okay, let's do it. Let me go to how about the 3 lambda? If you choose any t positive and theta t, just a single order motion, and m say t to be m tilde theta t, then this is factor of type 3 lambda. Right away, the fixed point of theta t is precise. Why? That's the 3 m tilde. It says, if you look at it, m tilde has a trace which scaled by theta sub t by exactly lambda, right? And it's a fixed point, so it is the 3 lambda. Or if you want a more complicated one, then you make a cross product relative to theta sub t, so that this is isomorphic, if you like, m tilde relative to sigma t and integer. That gives you 3 lambda. Either way, fixed point or the cross product, 3 lambda. So it's right away. And theta t, those are lined them up. 3t1 as let's see, t2 divided by t1 has to be integer. And at the end, at the end is the m. The fixed point under all one parameter automorphism. That's the 3-1. So what you have is lambda 1, lambda 2. So that means the logarithm lambda 1 over logarithm lambda 2 is in positive integer. And that's then lined up very nicely. And the intersection is, of course, m. So it's 3-1, if you have a core of 3-1, the 3 lambda factors are all lined it up. And the different, all of them are non-isomorphic each other. Okay. Now move on to this realization. TS, you have d mu associated with the flow is this rho of Sx, which satisfies the following S plus T, X is rho S TTS, rho Tx. That's the cocycle identity. Okay. This is our positive multiplicative group of real number. Now, what you do is consider n equal to m tensoring with C. That's the carrier of the flow. Carrier of flow. So, okay, let's write it because you don't know if this is the flow of weight one. So take it alpha. So that alpha SF of x equal to f of TS inverse of x. F is in C. And now we want to extend this alpha to this. Of course, the simple-minded alpha S doesn't work because if alpha preserves the measure mu, that work, suddenly it work. But if not, it doesn't work. You have to look at the point by point. So you realize then this algebra as infinity, m tilde values essentially bounded function over x mu. So element here is a of x, a of dots. Okay, so the m tilde valued bounded function and essentially bounded. Okay, that is the algebra. That is this n. Now, to specify the one-parameter morphism is then say the tilde S of A evaluated here. You have to do what is this theta of S minus log of rho Sx applied to A of Ts inverse. I think this should be I think this is inverse Tsx. Okay, this is a new definition. And then theta tilde S to the function f. Look at this one. Then this doesn't do anything, so this is a Ts inverse of x. So this is this is f this is alpha s of f evaluated at x. Right? So suddenly this theta tilde S is agrees with given flow alpha. So now when it comes to so we have to well, instead of writing f of x, the mu of x, I write Okay, so now, so I view mu as a weight on C or trace on C. So tau mu tensing with, no, tau, well, I think, oh yes, tau tensing with mu. This is our trace, tau tilde on n. And then evaluate what's happened. So what happened is that now theta tilde S of A, and I evaluate tau integrate and mu. And see if minus S pops out or not. So this is going to be integral over x tau of theta S tilde of x, A, evaluation at x, and the mu of x. That is the major tau tensoring with the mu. So I write down x. I know tau theta S minus logarithm rho of S inverse S of A of Ts inverse x, Ts inverse d mu x. Okay, that is just simple writing down, exactly the same thing right there, defined this way. Then we know that this is what? This one is equal to integral. The tau is scaled by trace, exact e to the minus s minus log rho s inverse comma x, and tau of a Ts inverse of x, the mu of x. That's what theta, the flow on the factor part is. So e to the minus s does not depend on point x, so e minus s goes outside of the integration. So this is e minus s integral log of minus minus plus and the exponential. So it goes rho of s inverse of x and tau of a over Ts inverse of x d mu x. I know this is it is the way it is Radon derivative, so this is tau of a over x d mu of x over x. This is precisely e minus s tau cancelling with mu evaluation of a. E minus s pops out precisely. Yes, so therefore, this n, r, and the theta tilde tau cross mu is a core of it's a fixed point. You have, then you make it as m, forget about the original one. Let's see. So this n and theta, say this is, if we call it, say p, then this is the 3-0 factor whose flow of weight is precisely the one you prescribed. CR, this C, the flow of weight is C, R, and alpha. So every ergodic flow, properly ergodic flow, appeared as a flow weights on appropriate factor of type 3-0. Now, if M tilde happen to be AFD, then the example you construct here out of M tilde, right? The theta T fixed point of M tilde, that is 3 lambda AFD factor. And if you make it to the coupled with this construction, then you have AFD factor of type 3-0 with given flow as the flow of weight. And therefore, this gives you the complete list of approximately finite dimensional factor of type 3. Okay, so namely, let me repeat. If you construct 3-1 factor. How? We did it already. Remember 3 by 3 matrix with long lambda, with long mu to be irrational. The ratio is irrational, and the infinite tensor product, and that becomes 3-1. And its core is 2 infinity factor, and 1 parameter automorphism scaling trace down nicely. So you have it one. It's right there, right away in the this M3C infinite tensor product relative to that lambda mu, long lambda, long mu, irrational. That was the precondition. And then you do this game, you exhaust all 3 lambda AFD factor, lambda 3-0 case, you couple with this flow weight, which the flow given to you. Unfortunately, nobody knows the whole list of ergodic flow. Okay, there's no, but as long as ergodic theorist gives you flow, you construct the 3-0 factor for them. So that's the situation. The people's name, the contributor is to this goal is the quite number of powerful persons. Notably, Kohn comes to the first, but his work is very much motivated Arake was, also Krieger, their renowned ergodic theorist, and for the 3-1, that's Hagerup. Kohn's, Arake was, Krieger, Hagerup, and Let me see. Oh, okay. You have to give the credit to the Henry died because he is the one started out of the orbit equivalence on the action of a group. And without that concept, nothing could fly. And Krieger picked up from there. So, and okay. Now, I mentioned informally that what we are doing is kind of number theory in analysis. Okay, let me give you the flavor of the number theory or the when that matter Galois theory. So now, this was, I think, construction of B sub P. Did I think I did this in the class, not in the afternoon class. This is in the class. Is it? Not the class. Otherwise, maybe. But at any rate, what happened is the following. Now, suppose for the Galois theory, maybe it's more appropriate to write in the M is M tilde cross product theta by Leo instead of a fixed point. Then what happened is the following. Remember, we see G1 theta of real line with the coefficient in the center. You had sigma phi C. Oh, no. C, not the theta. That's the modular automorphism. How this appears? Now, automorphism of M fixed in that core pointwise is precisely isomorphic to G1 theta of R U of C, one cocycles, and bias sigma phi C. Okay? This is one thing. How you do it, so if you, in this case, you are writing this way, M tilde, and you have center C. So this M is generated one parameter unitary group, S in real line, such that R the US equal to theta S. That's the way it is constructed, right? So, automorphism which fixes M tilde. Now, M tilde is a subalgebra of M. So, how you define this one? Phi is, this moment I write it, phi is tau hat. That's called the dominant weight. In that case, that the fixed point, the modular automorphism is the dual to theta, so this is M tilde. The centralizer of phi is M tilde. Okay. Then, in this picture, what's happening is M tilde to the relative commutant in M is once again, this is C. The center of M tilde itself. It's a very strong tie. And M, if you are in the opposite setting, M being a fixed point, its relative commutant is C also. In this case as well. Oh, excuse me. This is a scalar. No, C is not a subalgebra of M, please. This is a scalar. M tilde as a relative commutant inside M is called scalar now. And what's happening is, wait a minute, M tilde inside, oh, excuse me, yes, this is indeed C. Yeah, C is a subalgebra. I'm confused which way we are considering. M is it's one step up. So with this, then they're very easy to analyze alpha of U of S and use S star has to be in the center. This is C sub S. That's a Z1 of theta of RUC. And that's why alpha of US equal to CS of US. That's the way sigmas, the extended modular of the morphism pops up in the flow weight joint paper with Alan. And now, so this Galois group is precisely this cocycle group. And it is in if and only if it's cobundary. It's very present. It's algebraist will be very pleased. They like thought statement, such statement. Now, now I want to move on. Remember, M is, okay, we constructed M tilde as and C. Oh, actually, how it was started, it's M tilde was 3, 1, so we started to be N. Okay, back to the original setting. Okay, back to the setting. The M tilde is to infinity factor, and theta tau cross mu is tau tilde, and theta is tilde precisely transforming trace in exactly the way we want. T tau equal to E minus tau tilde. Now, when you have construction of anything from a certain data, yeah.
What is C?
C. Remember, this M tilde was to infinity factor. That's the very beginning. We have the real line theta tau, theta s e to the minus tau. So we have to work a little bit to invite center C and the flow over it. Okay, so that's the setting. Now what I'm saying the following. Whenever you have certain construction out of given data, very often you have a symmetry in a given data. Okay? When you have such symmetry, don't ignore it. You have to see to what extent that symmetry reflects on your object you constructed out of data. Okay? Don't forget that. That is a must. This is general strategy. Okay? General strategy. When this is not only just applied to this particular situation. This is all over mathematics. When you have anything to construct, and then out of a certain given data, that given data often carries a lot of symmetries. Then you have to look for how that symmetry reflects on the object you constructed. Now, what is the symmetry to our data? It's definitely automorphism which commute with the flow. So, automorphism which commute with theta is those alpha automorphism of C such that alpha theta S circle alpha. That is the group of symmetry of flow. So as we constructed the 3-0 factor, then we have to see how it reflects. Okay, given alpha, we have non-singular transformation on X, which has the non-singular, so you have rho function, rho alpha. And once again, this satisfies the cocycle identity relative to the group of all automorphism commuting with theta. Of course, you don't need theta, but unless it commutes with theta or the action of flow on the center, then that doesn't make sense. So, now, you do the exactly same way, but now this time, alpha tilde of A, evaluated X, A is in L infinity, and valued function over X is theta minus log of alpha inverse of X, here rho of alpha inverse of X of A of T alpha inverse of X. Okay, well, by the way, alpha of F evaluation of X equal to F of T alpha inverse of X. That's what it is. Okay. Then you see right away if you look at this alpha tilde, what's going to happen? This now to preserve the trace because we don't have S. Remember that the S minus S here shift the trace by E minus S, and this one served as the one preserves the trace. Okay, so so alpha tilde belongs to automorphism which commute with theta tau m tilde, which is the group such that alpha theta s equal to theta s alpha or s in real number, and alpha tau has to be preserved. And this mapping obviously C to alpha tilde is a injective homomorphism. Injective homomorphism. And this automorphism group, this when you restrict the element here to the m fixed point of m tilde, m tilde theta, then no, this is the n. This is the n. No, this is the n. How I write it? Okay. So this is n tilde. This is n. Okay. So this is n, fixed point under theta. Okay. Then what happened is this alpha tilde, this from this automorphism alpha restricted m. Okay, alpha commute with theta, so it alpha the restricting to the n theta makes sense. This makes sense. At the same time, this trace preserving property gives, if this is identity which force you alpha is original automorphism identity. So the automorphism in M, automorphism M characterize actually the precise the restriction of those automorphisms of N commuting with theta, preserving the trace. Okay, commuting with theta, then the theta, some member of theta, theta sub t, commute with it, but it does not preserve the trace. Okay, so that's the very strong property. This is precisely equal to aught m theta. So trace plays definitely important role. Without trace fixing property, you have then you have no way to describe the group of automorphism of the fixed point. Yes.
So the last line you said that alpha restricted to n theta. The last line.
Yeah.
Alpha restricted to n theta is identity implies alpha is identity.
Yes. Alpha to the fixed point, the identity plus trace preserving property implies alpha equal to identity.
Because there is some conditional expectation, is that the reason?
Yeah. So that is the very strong characterization of the automorphism of the fixed point. Let me see. At any rate, okay. So let's return to the original claim that whenever you have a symmetry of the data, that's this automorphism, the flow, automorphism commuting with theta, lifted to the automorphism of n, which preserves a trace commuting with theta. Therefore, that alpha tilde is indeed automorphism of n upper theta. Precisely, so you are done. Symmetry in the data gives you the symmetry in the the product. Okay, so as a philosophy, mathematical philosophy, you have symmetry of data gives you symmetry of your object, constructed object. And indeed, I witnessed many people forget about this important agenda, symmetry of constructed object. Constructed object. Okay, so many people forget this. And now, what is the byproduct of this? Okay, this alpha of your origin theta gives you alpha n of theta tau of n. Oh no, this is n theta. And this restriction is called mod alpha, which is it's commuting with automorphism of theta. Okay, this is a new notation. This is the modulus of alpha, how it behaves. And now you will see the procedure I did is the opposite of that arrow, right? Opposite. So what that means is this, particularly this mod sequence has the inverse. That the construction was the inverse of that mod function. So that's, and the construction is nicely that homomorphism, multiplicative. So that means this is kernel of modulus map, then map into that, the kernel appears, and then coming back, semi-direct product by auto theta of C. That is the result we gained out of this analysis. So, so this is indeed your automorphism of your factor. Your factor, 3-0 factor. Or, well, it's there's no need, of course, 3 lambda factor, it's the same, but it's 3, yeah. So, this is a semi-direct flow. Of course, this is not a unique semi-direct product because that's this canonical extension. If this is okay, there's other way of the extension. There can be other way. So this is not by no means the unique semi-direct product. product. But of course, this one is unique. This one is unique, but the mode inverse, there are several ways to have it. So this is the structure of group of automorphism. Analysis of a group of the symmetry is very important. That is ever since Galois, the 19th century, is the central theme of modern mathematics. Don't forget the symmetry. Look at the symmetry all the time. So factor to analyze, first things to do is look at its symmetry. That means group of automorphism. That is the lesson we learned from Galois, Abel. Okay, that is the mathematicians, the new tradition, which were not there before Galois. Okay. Oh, yes. This, well, this construction itself is not a different, but the result itself are given by who? It's a bit of a surprise indeed. It was Robert Wong, the student of Korean Sunderland, in his thesis at the University of New South Wales in Sydney. And the paper was, of course, accepted. But what happened is the paper was accepted, but it was not processed right away. If you have the, okay, from editor to the, it was transaction, so that MS headquarter, okay, sent. And then the transaction had a backlog, so some time passed. And then when it comes to the paper's turn, MS sent to Wong copyright agreement letter, which never answered because the Wong has left the Sydney after PhD, possibly in despair on the job market as of that time. He did not get a decent job, and he went back to Hong Kong, left academic life, and that the AMS cannot go to publish without consent from the author. So that the paper itself is sitting in the warehouse of the AMS, never appeared. So knowing this, Colin and myself took a pain of writing up. The result appeared in somewhere. I think it's in the literature list of the. So the proof, it's not appeared as a Wong's paper, but in the joint paper of Sutherland and myself. Okay, though we didn't claim any originality. That's a Wong's result. This very simple construction is possibly byproduct of our attempt of constructing, understanding the automorphism group, action amenable group. But this is about the factor, yes. Now, okay, this is about the structure of, let's say, where are we? Let me take a look. I think this is about what I prepared. Yes. So we have still more than half hour, so maybe I make a little bit. once again, so given all this data, let's line up what we gain. In the middle, okay, you have M tilde and R theta and tau. Okay, we don't restrict anymore. M tilde need not to be a factor, and M is its fixed point. So this is the core of M. And then what happens is the following: the normalizer of M inside the unitary group of M tilde. Okay. Then you make the characterization for membership of U tilde is a coboundary. The coboundary operation relative theta send the element here into the cocycle. Right? So this is the one relative to theta of real line of U of C. And this is surjective. And coboundary, that coboundary, this is surjective. So this theta of U evaluation T is U star theta sub T of U. U of unitary of M tilde in general, but when this belongs to the center, this belongs to the center if and only if you normalize the M. And this kernel means this equals, that means that U is fixed under theta T. So the kernel is fixed means indeed unitary of M. And this is injection. Okay. In this one, here you have unitary of center, suddenly is a subgroup. And if you have cobounding, this is going to the coboundary. That's the definition of coboundary. And it goes in, and this is is injective. And if you mod by this one, by the coboundary, but the cocycle divided by coboundary means that's a cohomology 1 theta of R U C. And center of that is called cent sub R of M, and this goes to actually the dot theta, and this is by definition this is the image always. Then torus is here. We are talking of a factor, and this is the embedding. This is if you divide this unitary group by this scalar, you end up with the inner morphism. And this is surjection, so 1. And this is also this surjection. This is the surjection. So this is we name this one the characteristic square. For M. Okay, and except 30 case, all group Polish. And the 30 case, except this one, all are the Polish group. Well, we are talking of always the separable phonemic algebra, means separable predual. Maybe this is exercise. Phonemic algebra, which is separable in no, is finite dimension. Is it surprising? It's a try. Non-separable phonemic algebra is finite dimension. Hint is the following. Infinite dimensional phonemic algebra contains infinite orthogonal projection, infinite many orthogonal projections. If there's no such thing that has to be finite dimensional, that you have to prove. And if you have infinitely many orthogonal projections, then little L infinity is inside. Little L infinity cannot be separable. Okay, so what you need to work is the existence of infinitely many orthogonal projections, non-zero orthogonal projections. Okay, so we are talking of all the time separable phonemic algebra, unless something occurred to the necessity. That is an ironic fact in operator algebras. If you want to restrict yourself to the separable phonemic algebras all the time, but you cannot, indeed, because of the ultra product technique, which is very powerful, and you cannot ignore it. That is actually appearing in even for the uniqueness of the say AFD factors or type 2 infinity or 3-1 factors. You need non-separable phonemic algebras to prove a theorem on separable phonemic algebras. Okay. So that's, well, that is the life. That's the life. So let's look at this middle. Oh, this is one column. So let's do it in horizontal because so you have the abelian group sitting in a non-commutative group as a central subgroup and the normal subgroup of G. And this is G equivariant. Okay, what is the group G? G is here automorphism group of M acting on this one times real line through theta. It's an equivariant. Those squares are equivariant commutative square of exact sequences. So, and n acts on A trivially. Let's see what happens. Suppose you have S of M, a cross section, so that J of S of M equal to M. Okay, when you are in this setting, you don't want to use M on the set for the automorphism. So, but for this abstract setting, you can't do. And then what happened is Sn equal to mu of Mn S of Mn. Mu is in the center. It's so-called two cocycle. And alpha G of S of G inverse M G will be, this, if you map this into N, then this is the under J, then this will be G inverse M, G inverse. That's, because this is a covariant, equivariant, so this is M. So alpha J S of G inverse M G equal to lambda M G, the member of A, S of M. So you have lambda mu, the pair. Mu is two cocycle, lambda is a new gadget, something, obey certain rule. And set of all of this is the Z of group G and the value in A. Characteristic cocycle called. And its class is, well, naturally, if you change S prime M by function M, S of M, then that implies mu prime will be co-boundary of times mu. And lambda prime is second of lambda 2. That's easy to check. So this cohomology class, and so those are the co-boundary of G and A. And the divide, that's a characteristic cohomology group of this triplet. Okay? And because this is intrinsically associated with M, you have this class, the cohomology class, lambda mu. That's chi of M. Sitting in that case, this is a mod times theta of automorphism of M cross R, and the center of, what is the normal subgroup? It's a U of C, yes. Normal subgroup. No. Normal subgroup appears on the last end. Yes, this is N. CNT R of M and the coefficient of a unitary group. This is the common. This is called the intrinsic, because invariant of M. And whenever you have a group act on M, the automorphism, then you pull back that cohomological element to your group. That's cocycle conjugacy invariant. Okay, and when M is AFD, then that cohomology invariant plus mod, that's how it acts on the center, And this cross-cycle invariant is complete invariant for the amenable countable discrete group action on AFD factor. Okay, and I think we have spoken about it in the afternoon session. And okay, I stop here. And first, thank you. Well, before closing, is there any question?
There you said that G is odd M cross R.
You mean this one?
No, just next to that. Yeah.
Yes.
Yeah.
This is R octon theta.
Yeah.
Yeah.
And you're taking this sequence, so that will mean that the that group must be normal.
Come. Don't hesitate.
So this must be normal here.
This is acted by the conjugation.
Yeah. So, but this is conjugation by elements from the normalizer of M in M tilde, right? This one.
Exactly.
Right?
Yeah.
But that should mean that any automorphism here should be, you can lift it to the normalizer, then this will become normal there. This subgroup.
This is a normal subgroup. This is a normal subgroup of auto M.
Because here you can lift any automorphism to the centralizer.
Any automorphism acting lift out here by as the member of theta tau of M tilde.
Okay. Then it's
Thank you for coming up. Any others? Then I would like to express my appreciation to the Sundog giving me this opportunity of delivering the series of lecture. Thank you.